We were doing functions of two random variables, a random variable that is a function of two other random variables. Um, and in a previous video, I did one example. Uh, given that we have the PDFs of X and Y, and we have this relationship, R squared equals X squared plus Y squared, what's the PDF of R? And we did that example, and the procedure, again, to repeat the previous video, is to find the CDF of this R by integrating over a region in the XY plane of the joint PDF of X and Y. And the region is where this condition is true. Uh, Kind of follow this logic. We're looking for the CDF of the random variable we're interested in this case, that means the probability that it is less than an argument, the random variable is less than an argument, that that random variable is a function of the other two random variables. In this case, or in that case, it meant this. The region of integration was where this was true, where x squared plus y squared was less than some. Here was the joint PDF. Here was the region we had to integrate. In that case, we used polar coordinates. I won't go through that again. Well, let's do a second example. Here, the x and y are independent, each distributed uniformly from 0 to 1. And we want LZ just as their product. What's the PDF of their product? Well, they're independent, just uniform. So the joint PDF is just a unit cube. And the XY plane is just this square. They're each distributed from 0 to 1. Here's what we need. CDF of F, excuse me, the CDF of Z, that's where the probability of Z is less than or equal to some argument. Z now is equal to this product, and that equals joint, or the double integral over the joint PDF. The joint PDF is just 1. You know, it's the product of these two guys. So that's why it's a unit cube. So it's just 1 over the unit cube. So what is this region? Where is this true? Here's where a sketch helps. X, Y. I can write this as a function of y setting, y less than or equal to c over x. And that line would look like pick some z. And if you look at this, if x and y are each between 0 and 1, then z has to be between 0 and 1. Well, if you pick some z between 0 and 1, it would look like this curve here. And the region you integrate over then is where y is less than or equal to that z over x, which would be this shaded region down here. So all we need to do is integrate this very simple looking integral, double integral, where this is the region. Well, the easier way to do that is actually do 1 minus the integral over this region. Otherwise, we'd have to split up this region to do a double integral over the strictly shaded part. So we'll find this area, or that's where we're going to integrate over. And we're just integrating up to 1. So here's kind of the tricky part of this problem. What are the limits? I'll do it so I integrate over y first. Then y will go from this z over x up to 1. You know, pick any, for a given z, y will go from like there up to there. Z over x up to 1. And where does x go? Well, x starts at wherever this is. And that's where y equals 1. So that's where x equals whatever your z is. So the limit on the x variable is from z to 1. So here is your setup. This is all kind of a tricky, semi-subtle double integral problem. Once we have this, we're doing just normal double integration. Here we have to actually iterate. It doesn't break up into a product. We have to iterate. So we have to take the integral first. That's how you get this. And this is an integral of a sum. So you do that. I'm not going to go through all that. Finally, after some simplification, you get this. Z times 1 minus the natural log of z. I don't think you would have ever come to that. I don't think you would have ever thought, just by looking at this, that's what it would look like. And then once we have the CDF, we get the PDF just by taking the derivative. So we have to take this little derivative of a product. I won't go through that either. And here you get this thing. And of course, Z has to be between 0 and 1. It's 0. PDF is 0 outside of that. So there it is. You sure could not have intuited that. That kind of pain was when you had to get the entire PDF of the result. If you're only interested in moments, you don't have to go through that much pain. Like we did this example a little earlier of just a single random variable, a function of another random variable, and you had to find the whole PDF. All you need is to find, say, the mean and the variance, or the mean and the mean square. You don't have to find the PDF and then calculate from the PDF. You just go right to those moments. Expected value of y, since this is the functional relationship, expected value of x squared. Now you just do it the normal way. It's the function x squared integrated with the PDF over all x. So in this case, you put that integral. And if of y squared, that now means x to the fourth, which will mean, where's the 1/2 component? That's the PDF. Here's the PDF, 1/2, function of x to the fourth, and it goes from -1 to 1. So it's if all you need to do is get the moments, don't go through the pain of finding the entire PDF. I'll save this last part for another video. But if your function of two random variables is a sum, just x plus y, we're going to find out there's a possibly easier way to do it than what we just did. And I'll save that for another video.